there's a 90% chance of recovery, so that's p, 0.9. Okay. So because we're counting successes, because we have independent trials, because we have 2 outcomes, and we have multiple trials, altogether this means that we can assume big X follows a binomial distribution. And in this distribution, the number of trials n is 7, and the probability of success is 0.9. Because these other things are true, this statement is true. And when our variable follows a binomial distribution, then we can use that binomial PDF function in the calculator. If we don't know that this random variable is binomial, then we can't use the binomial PDF function. So now we get back to the question. How many of the next 7 patients can be expected to recover? So what this means is we want to know the mean of this probability distribution. On average, how many patients will recover in the next 7 surgeries? So from page 8, we see that we have this statement. And I went over it before, but I didn't specify. So this weird u, we have seen this before. That's the Greek letter mu. That means this is the mean of the distribution. So if we want the mean of a binomial random variable, we just take n times p. And because we have the binomial distribution, we can use that formula. We don't need the whole probability distribution. We don't have to do x times the probability plus x times the probability, etc. This formula works. So in this case we have 7 times 0.9, which is 6.3. So on average, 6.3 of the next 7 patients will recover. And you could say we expect, or it's expected that 6.3 of the next 7 will recover. Okay, so this is good. There's a high probability that they will recover. There's a 90% chance to be successful. So we should see a lot out of the 7 recover. It's a little more than 6. Okay, and again, it's okay that the mean is not a nice round number. Next question, what's the standard deviation for the number of patients that will recover? Okay, so we're trying to get a feel for how spread out is this probability distribution. So what we want the standard deviation, and we saw that's the square root of variance. So again, from page 8, there was that formula for variance. So we want the square root of n times p times 1 minus p. So we want the square root of 7 times 0.9 times 0.1. So again, 1 minus p, that's the probability of failure, that they don't recover. 1 minus 0.9 is 0.1. So we know that we have 7 times 0.9 is 6.3. So that's what we just did above. Times 0.1 is 0.63. So now we want the square root of that. So if you have a TI-83, the square root is over here above the x squared. So you have to press second x squared. So you get 0.7937. So what this means, thinking back to when we initially defined standard deviation, this is saying that on average, the number of patients that recover will be within roughly 0.8 of the mean, 6.3. So putting that together, this means on average, we would expect between a little over 5 to 7 patients to recover. That's what the standard deviation means. How spread out are the number of recoveries around 6.3? Well, they're pretty close. The number of people that recover should be pretty close to 6.3. A little above 5 and just a touch above 7. So we'll just kind of truncate it. We'll cut it off at 7. Okay? So that's what the standard deviation tells us. What's the probability that exactly 5 of the next 7 will recover? Okay? So the word exactly means that's all we want, just 5. No more, no less. So what we're saying is we want the probability for big X to equal 5. We want 5 successes in the next 7 trials. Okay? We can find this using the binomial PDF now. The binomial PDF is meant to find these types of probabilities. It is meant to find probabilities of X equals something. This formula here is binomial PDF. It computes all of this as we showed. So if we want to find the probability that X is 5, we can use the binomial PDF. So we know that N is 7, P is 0.9, and we want 5 successes. So second vars, go to the binomial PDF. N is 7, comma, P is 0.9, comma, and we want 5 successes. And there you go, 0.1240. Okay, so what does this mean? This means something like there's a 12.4% chance that exactly 5 of the next 7 patients will recover. So let's think for a second. Does that seem right? We have a 90% chance of success. Does it make sense that there's a 12 and change % chance for 5 people to recover? The answer is yeah. And it's about what we're actually looking for. Okay. So what this means is if we have a 90% chance of recovery, well then we expect that 6 will recover. That should be the most likely value. So what we're asking is, well, what's the chance that 5 recover? So below what we expect, and more specifically, we want exactly 5. What's the chance that only 5 of the next 7 recover? That's a very particular outcome. So since it's specific and it's below average, its probability can be low. Okay? So this does make sense. There's only a 12% chance to see 5 survive, or recover, I guess, and 2 not recover. So one more. What's the probability that at least 5 of the next 7 will recover? So we see this word, at least, and we have to be cautious. So we can rephrase this. What's the probability that 5 or more of the next 7 will recover? So this means we're looking for 5, 6, or 7 recoveries. Any of those will be fine. We want at least 5 recoveries. 5, 6, or 7. So in probability notation, we're looking for what's the probability that X is greater than or equal to 5. Okay. So we want 5 or 6 or 7. So we can add all of those together. So we can rewrite this as what's the probability that X is 5 plus the probability that X is 6 plus the probability that X is 7. And we've already found the probability that X is 5. That's 0.1240. So now we just have to find the other probabilities. And we'll find them the exact same way we found the probability that X would be 5. So if we wanted the probability that X is 6, we can still use the binomial PDF function. So n is still 7, p is still 0.9, but now we want 6 successes. So get to your binomial PDF, 7, 0.9, and 6, and you get 0.3720. So the last one, the probability that we get 7 successes, again, we'll use binomial PDF. 7 trials, 90% chance of success, but now 7 successes. And you should get 0.4783, we'll call it. Okay. We've done a little bit of rounding. It's okay. We can be more specific if we wanted, but this will be okay for now. So now we just add these up. 0.4783 plus 0.372 plus 0.124. So you'll get something around 0.9743. Just depends on how much you rounded. 0.9743. Okay, and this is the probability that x is at least 5. So if we interpreted this, we'd say something like there is a 97.43% chance that, whatever the question asked, at least 5 of the next 7 patients will recover. And maybe this is an answer that seems more like you would expect, as opposed to when we just found the probability that x was 5. So 5 or more recoveries, yeah, so that's where we should be. The average was 7. We had a standard deviation of about 1, which said we expect to see on average between 5 and 7 recoveries. That's where most of the data should be, and that's what we found. There's a 97.4% chance that at least 5 of the next 7 patients will recover. And again, we found that just by breaking this down into separate probability statements and then using the binomial PDF. Okay, we'll do one more example, and then that'll be the end of this lecture. So I'm shooting for lectures to be right around an hour, maybe a little longer, and then we'll have the WebEx meetings for about another hour. That way you're not watching 2 hours of lecture and then you're responsible for 2 hours of online meetings. I'll try to split it between the two. So one more binomial example. So a traffic control engineer reports that 25% of the vehicles passing through a checkpoint are from out of state. What's the probability of that? Blah, 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 blah. We'll find out. So the first question is, well, what assumptions are needed to utilize the binomial distribution here? So if we skip down to what the next question is, what's the probability that exactly 2 of the next 9 cars are from out of state? We can start to get a feel for what we want. So if we think about what the random variable is, big X, that's going to be the number of out-of-state vehicles in the next 9. So we're checking the next 9 cars, and we're interested in how many are out of state. So what this means is we have 2 outcomes. We have out of state, which that's what we're interested in, so we'll call that the success. And we have in state. That's what we don't care about, so we'll call that the failure. And this question says, well, what assumptions are needed to utilize the binomial distribution? So we have one piece. We have 2 outcomes. So what's the second piece? The second piece is that we need independent trials. So a trial, in this case, is just a car. a car that passes through. And we have to assume that we have independent trials. So you can always make that assumption, but you need to take a second to think about, well, is it a valid assumption? Does it make sense? So does it make sense that the license plate of a car passing through has no effect on what the next license plate is? Say that we have one out of state come through, does that change the probability that the next car is out of state? And I would say in general, it has no effect. I think in general, independent trials are okay. A car coming through should not be related to the next car. Now there are some exceptions. If people are going on a road trip or something, or commuting together to a family or family member or something, then maybe. But by and large, in general, one car's license plate, whether it's in or out of state, should not affect any others. Okay? So we have independent trials, we have two outcomes, and we have more than one trial. So what this means is